NASA has used it to power deep space missions where no fuel delivery is possible. The United States military has used it to run silent submarine systems where engine noise means detection and death. New Zealand deployed it in over 800 homes as a combined heat and power unit generating electricity from a natural gas flame, at 40% thermal efficiency compared to 25% for the best gasoline generator available at retail today. It runs on the heat of a candle, it runs on sunlight, it runs on waste heat from a factory exhaust pipe. It was invented in 1816 and it has been commercially available and repeatedly cancelled ever since. Robert Stirling was a Scottish minister, not an engineer. In 1816, he was serving the Church of Scotland parish of Kilmarnock in Ayrshire when he filed British Patent 4081 for what he called an air engine, a device that converted temperature differentials between two chambers into mechanical work through the continuous cycling of a working gas. Stirling's motivation was not scientific ambition, it was the deaths occurring weekly in Scottish industrial sites where high-pressure steam boilers were exploding. His engine required no boiler, it required no high-pressure vessel. It required only a heat source on one end and a cooler surface on the other. The working gas, air in Stirling's original design, cycled between them, expanding when hot and contracting when cool, pushing a piston through each cycle as it moved. The Stirling engine ran its first industrial application at a Dundee quarry in 1818, pumping water from the excavation without a single pressurized vessel. It ran for 2 years before a manufacturing defect unrelated to the thermodynamic principle caused it to fail. The engine was refined across the 19th century by engineers who recognized its fundamental efficiency. Advantage was limited in practice by the materials available. Cast iron hot end components degraded rapidly, the working gas leaked through imprecise piston seals. Industrial development in the Victorian era consistently returned to steam because scaling steam pressure was a solved manufacturing problem. By 1900, the Stirling engine had retreated to a niche application. Small domestic hot air fan engines running on the heat of a kerosene lamp sold as parlor novelties. They existed by 1938. Philips Research Laboratories in Eindhoven assigned a team of engineers to develop a compact portable electrical generator. Their solution was a Stirling engine using hydrogen as the working gas, with precision machined components manufactured from high-temperature alloys that the aircraft industry had developed for piston engine cylinders. Philips's first hydrogen Stirling generator, completed in 1943, produced 200 watts of electrical output from a unit the size of a large briefcase. Its thermal efficiency measured 38%, nearly double the best diesel generators of equivalent output available in 1943. Philips filed over 700 patents on Stirling engine technology between 1945 and 1975. They licensed the technology to General Motors in 1958. General Motors operated a Stirling engine research program for 12 years before canceling it in 1970. Ford Motor Company took the license next. The Stirling engine works through a thermodynamic cycle that Lord Kelvin identified in 1851 as theoretically capable of achieving the maximum possible efficiency permitted by the laws of thermodynamics, the Carnot efficiency limit. No internal combustion engine, no steam turbine, and no gas turbine operates on a cycle that reaches this theoretical ceiling. The Stirling cycle approaches it more closely than any other practical heat engine design. The mechanism requires 4 components and no combustion inside the engine itself. A hot end, any surface maintained at an elevated temperature by any heat source whatsoever. A cold end, any surface maintained at a lower temperature, typically by ambient air or water cooling. A working gas sealed inside the engine, historically air, in modern high-performance versions hydrogen or helium, that alternately contacts the hot end and the cold end as the engine cycles. And a regenerator, a porous heat exchange matrix, typically fine wire mesh or metallic foam, positioned between the hot and cold ends, that captures heat from the gas as it moves toward the cold end and returns it as the gas moves back toward the hot end. The regenerator is the critical component that conventional descriptions of the Stirling engine consistently underemphasize. Without it, a Stirling engine is merely an inefficient heat engine. With a well-designed regenerator, the engine recycles 70 to 90% of the heat that would otherwise be lost during each cycle, recovering thermal energy internally before it can dissipate, which is thermodynamically equivalent to running the engine on a fraction of the heat input it would otherwise require. NASA's Advanced Stirling Radioisotope Generator, the space power system developed by SunPower Incorporated of Athens, Ohio, under a Department of Energy contract, achieved 38% conversion efficiency from heat to electricity, using a free-piston Stirling engine with a precision wound wire mesh regenerator. The radioisotope heat source it was designed to use generates approximately 250 watts of thermal power. The engine delivers approximately 100 watts of electrical output. The best thermoelectric generators currently used on NASA spacecraft, the technology the advanced Stirling was designed to replace, convert the same heat input to electricity at approximately 6 to 8% efficiency. The Stirling engine outperforms the best alternative NASA uses in space by a factor of 5 to 1. On Earth, it outperforms a gasoline generator by 40%. It runs on the heat of any source that maintains a temperature differential across its two ends. But does it perform under real conditions in real homes, powering real electrical loads? Whispergen was a New Zealand engineering company founded in Christchurch in 1995 by a team of mechanical engineers who had spent a decade developing micro-Stirling combined heat and power units for residential use. Their product, the Whispergen domestic CHP unit, used a 4-cylinder wobble-yoke Stirling engine running on natural gas or LPG. To simultaneously generate 1 kilowatt of electrical output and 7 kilowatts of thermal output for space heating and domestic hot water, from a unit the size of a large domestic boiler, E.ON, at the time one of the largest utility companies in Europe, contracted with Whispergen in 2008 to trial 800 units in British homes as part of a distributed generation program. The trial documented electrical generation at costs of approximately 8 pence per kilowatt hour at then current gas prices, below the UK retail electricity tariff, while simultaneously supplying the home's heating demand from the engine's waste heat output. Homeowners in the trial reduced their combined energy bills by an average of 20 to 30% annually. E.ON concluded the trial, filed the results, and did not proceed to commercial rollout. Whispergen entered receivership in 2013 after failing to secure the manufacturing scale contract that commercial deployment would have required. Qnergy, formerly Infinia Corporation of Kennewick, Washington, manufactures free-piston Stirling generators for remote power applications. Where diesel fuel delivery is prohibitively expensive, their QB45 generator unit produces 45 watts of continuous electrical output from a propane heat source with a documented mean time between failures exceeding 80,000 hours. More than 9 years of continuous uninterrupted operation with no maintenance intervention. The United States Army Research Laboratory evaluated the QB45 for forward operating base power supply in 2018, confirming its documented reliability figures. The evaluation noted that equivalent diesel generators require maintenance every 250 to 500 hours of operation. Qnergy's units require none. In Lund, Sweden, researchers at Lund University's Department of Energy Sciences completed a performance evaluation of a solar-powered Stirling engine system in 2019. A parabolic dish concentrator focusing solar radiation onto the hot end of a 25 kilowatt Stirling engine. Their published results confirmed solar-to-electricity conversion efficiency of 29% across the full operating day, more than double the conversion efficiency of photovoltaic panels. The dish Stirling system produced electricity at a measured cost of 11 euro cents per kilowatt hour without any fuel input of any kind. The photovoltaic system at the same site produced electricity at 14 euro cents per kilowatt hour including inverter losses. The Department of Energy funded automotive Stirling engine development through Ford Motor Company and AM General Corporation from 1978 to 1988, committing over $40 million to a program that produced a documented automotive Stirling engine achieving 40% thermal efficiency, compared to 25% for the gasoline engines in production vehicles of the same period. The program was canceled in 1988. The results were archived. Every test confirms the same efficiency advantage. Every application demonstrates the same reliability edge. So why does the world continue burning fuel in internal combustion generators running at 25% efficiency when a 200-year-old thermodynamic cycle routinely achieves 40%? The global portable and standby generator market was valued at approximately $6.8 billion in 2023. Honda Power Equipment, Generac Holdings, Briggs & Stratton, and Cummins collectively supply the majority of residential and light commercial generator units sold globally. Each company's generator product line is built around internal combustion engines, gasoline, diesel, or natural gas, running on a thermodynamic cycle whose efficiency ceiling was established in the 19th century and has not materially improved since. A gasoline generator consuming 1 liter of fuel to produce 2 kilowatt hours of electricity has been the commercial standard for 60 years. A Stirling engine consuming the same heat input produces 2.8 kilowatt hours from the same fuel. The additional 0.8 kilowatt hours generates no additional fuel sale, no additional maintenance call, and no additional filter or spark plug replacement. It simply disappears from the revenue model. The Underwriters Laboratory Safety Certification Standard for Portable Generators, UL 2201, was developed with input from Honda, Generac, and Briggs & Stratton. Its test procedures cover internal combustion generators specifically. A free-piston Stirling generator cannot be certified under UL 2201 because the standard contains no test protocol for an engine with no crankshaft, no ignition system, and no exhaust emissions in the conventional sense. Without UL certification, a Stirling generator cannot be legally sold through standard retail channels in the United States and cannot be specified by licensed electrical contractors for residential standby power applications. The Department of Energy's Automotive Stirling program, canceled in 1988, produced research results that were never commercialized. The National Renewable Energy Laboratory's Concentrating Solar Power program funded dish Stirling development through Infinia and SunPower Corporation through 2013 before shifting its research budget allocation toward photovoltaic cost reduction, a technology whose supply chain was being rapidly scaled by Chinese manufacturers and whose price per watt was falling faster than any Stirling commercialization program could match. The Stirling engine was not abandoned because it failed. It was deprioritized because a competing technology was falling in price faster than the Stirling could achieve manufacturing scale. SunPower Corporation of Athens, Ohio, not the solar panel company of the same name, continues manufacturing free-piston Stirling engines for specialized applications and holds the most comprehensive Stirling engine patent portfolio currently active in the United States. Qnergy's QB series generators are available for direct purchase for off-grid and remote power applications. DIY Stirling engine kits sufficient for small-scale electricity generation are available from multiple manufacturers at retail prices ranging from $50 to several $100 and require no specialist licensing to operate. No one sat in a room and decided to ban the Stirling program to protect the generator industry. A solar price curve made the decision for them. The generator standard was written before the free-piston Stirling existed. Neither outcome required a conspiracy. Both outcomes produced the same result. When Texas lost power for 4 million households during Winter Storm Uri in February 2021, when natural gas pipelines froze, wind turbines feathered, and gasoline for portable generators sold out across the state within hours, a Stirling engine sitting on a back porch needed none of those things. It needed a temperature differential. The difference between the freezing outdoor air and the warmth of a small propane flame is a larger temperature differential than Robert Stirling's 1816 engine in Dundee ever operated on. The colder the crisis, the more efficiently the Stirling runs. The conventional generator sat silent, waiting for gasoline that wasn't coming. The Stirling engine would have kept generating through every hour of the storm. The generator industry spent $6.8 billion last year selling engines running at 25% efficiency. Phillips Research Laboratories documented 38% efficiency in 1943. The Department of Energy confirmed 40% in automotive testing in 1988. NASA confirmed it again in deep space applications, where there is no alternative, and failure means the mission ends. Robert Stirling filed his patent in a Scottish parish in 1816 because steam boilers were killing workers. The engine he designed to replace them still outperforms what replaced it. The question was never whether it works. The question is why we're still asking why we don't use it. Subscribe now so you never miss the next solution the world forgot to use.